So to start with here, I want to remind you about what it means to simplify one of these. Now, notice it does not say evaluate. If it said evaluate, you would punch it in your calculator and figure it out as a decimal. That's not what it says. It says simplify. Now, when it says simplify, that means we have to go back to what a simplified fraction really means. And one of the things we learned about that is we can't have a radical in the denominator. So in the case of number 1, I have to get rid of that root 2. Now, to remember how we do that, the way that I can undo a radical is by squaring it, or in other words, multiplying it by itself. So I'm going to be multiplying the bottom of this fraction by root 2. If I multiply the bottom by root 2, though, I also have to multiply the top by root 2. Now, when we do that, on the bottom, what is the square root of 2 times the square root of 2? Well, that would give us the square root of 4, and the square root of 4 is 2. So that's why the radical goes away there. On the top, I'm doing 1 times root 2. Of course, 1 times anything is just itself. So the top then is root 2. That is now considered simplified. Now, it's considered simplified in case you're curious, because a lot of people are like, wait, doesn't that look more complicated? It's not a matter of how complicated it looks. It actually goes back to the idea of if you're having to do this out longhand, it's a lot easier to do some big decimal divided by 2 than it is to divide by some big crazy decimal, which is what root 2 is. All right, so now with that in mind, use that same technique to simplify 2 and 3. All right, let's check out number 2 then. So on number 2, again, I got that radical in the denominator I got to get rid of. So I'm going to multiply top and bottom of this one by root 5. When I do that on the top, 30 times root 5 is literally just 30 times root 5, so 30 root 5. On the bottom, root 5 times root 5, that's the square root of 25, which is 5. But now with this one, notice there's actually a little bit more we can do, because our fraction here can reduce. Now, it doesn't reduce because of this root 5 here. That root 5 could only reduce with something else that was inside of a square root. But the 30 and the 5 that are outside the square roots, those can reduce. What can I divide both 30 and 5 by? 5. So let's do that. So 30 divided by 5 is 6. The root 5 is still there because we can't do anything to it. And then that's over 5 divided by 5, which is 1. Now, we don't really need to write over 1 though, do we? Because anything over 1 is just itself. So then that gives us 6 root 5. And finally for number 3, same kind of an idea. I'm going to multiply top and bottom by the square root. So I multiply top and bottom by root 20. And so that gives me 16 root 20 over 20. And now we can look to simplify again. And if you look at the 16 and the 20, yes, we can divide both of those. Both of them divide by 4. So that's going to give me 4 root 20 on the top. And if I divide the bottom by 4, that gives me 5. Now what makes this one even a little trickier is it's still not completely simplified, because of that root 20. Now let's go back and remind ourselves, how do we simplify a radical like root 20? My technique is I break it up into 2 other radicals. What's the biggest perfect square that goes into 20?
4.
It is 4, yeah. And 4 times what is 20? 5. And so that's how I know what to break it up into. I break it up into 2 pieces. One of them is the biggest perfect square. The other one is whatever that happens to multiply to. All right. Now the reason why I look for perfect square is because I can take the square root of it. So the square root of 4 is 2. Then the root 5 just stays root 5. So going back to my problem then, my 4 root 20 becomes 4 times 2 root 5. And that's over 5 now. Now since we're multiplying them, yes, I can actually multiply the 4 and the 2. If it was adding, no, I couldn't because they're not like terms, but multiplying, they don't have to be like terms. So that's going to be 8 root 5 over 5. And then that is as good as it gets. That does not simplify it all past that, because the 5 that's inside the radical, it is trapped inside of that radical. And so it cannot work with something that's outside the radical like the 5 on the bottom. So final answer, 8 root 5 over 5. So the last assignment I gave you was going back to trying to remember what sine, cosine, and tangent were all about. That's because that's what we're heading into next. We're going into a unit on trigonometry. Now, all the information you see up here, this is all based on what we call right triangle trigonometry. This is what you saw at the end of geometry. Now, hopefully it's all review, but of course sometimes we forget things, so write down anything that you don't remember from this. And as you're doing that, to let you know, we're going to start with this right triangle trigonometry to, freshen up the skills you have from geometry, but we're then going to be extending it into what's called unit circle trigonometry. And that's where we're going to be heading with this. So today's going to be kind of a crash course review of trigonometry and how we use sine, cosine, and tangent. And then we're going to be continuing to build on that knowledge in the future. All right, now up here, some important pieces for you to see and note here. First of all, the labels on our triangle. When I'm having to label a triangle like this, the first thing I always look for is the hypotenuse. Now the hypotenuse is always opposite the right angle. You can also remember that it's the longest side in our right triangle. Both of those tell you hypotenuse. Now once you know hypotenuse, we got to know opposite and adjacent. And opposite and adjacent will move depending on which angle you're going from. Now in this particular problem, notice I've labeled that angle in the bottom left as being the one we're going from. That's why this is labeled as the opposite, because that side is on the opposite side from that angle. And then the adjacent side is the one that is next to the angle. Now you might be wondering, wait, aren't there two sides next to the angle? Because there's also this one. Yes, that one is also next to it, but it's the hypotenuse. So it's the one that's next to it that's not the hypotenuse for adjacent. And again, remember, that would change if I were going from this angle up top instead. So you always have to be cognizant about which angle you're going from when you do that labeling. All right, now knowing that, that's where the opposite, adjacent, and hypotenuse comes from in our definitions over here. Now these are actually called the definitions of sine, the definition of cosine, and the definition of tangent. Now do you remember how we remember the definitions of sine, cosine, and tangent? Yep, SOHCAHTOA. Now, if you're not familiar with SOHCAHTOA, of course you want to write that down, but let's see how we use that. The S stands for, so that's sine there for the S. O is actually one of those side lengths. Which side length starts with O? Opposite. And H is also a side length. H stands for hypotenuse, which tells us that sine equals opposite over hypotenuse. Okay, continuing down SOHCAHTOA, what's the C stand for? Cosine. Yep. And the A stands for adjacent. And of course H is still hypotenuse, so that tells us that cosine is adjacent over hypotenuse. And finally the T. T stands for tangent, absolutely. And the O and the A, they still mean the same things they did before, opposite and adjacent, so tangent is opposite over adjacent. So we can use SOHCAHTOA as a way to remember those definitions of sine, cosine, and tangent. They're going to come up a pretty decent amount here over this unit. Now with those definitions of sine, cosine, and tangent in mind, we're going to be using that information to answer these 4 questions. Please write down these 4 problems and the picture with room to work each problem out. And then we're going to work each of the 4 problems together so we can see what they're going to look like. All right, so let's do number 1 here. So the first thing I always want to do when doing one of these problems is to label a picture. So let's do that. First up, I'm told that C equals 70 degrees. Now notice it's a capital C. In geometry, you learn that capital letters always represent angles or vertices. So then the 70 degrees is angle C. B is 10. Now notice it's a lowercase b. Lowercase always represents a side length or a side. So then I know that B is 10, And then it's asking us to find C. Now I label my picture first because then that allows me to figure out which of the trig ratios I need to use, sine, cosine, or tangent. In order to do that, going from my 70 degrees, I label each of those two sides with their name. So side B, is that the opposite, adjacent, or hypotenuse? It is the hypotenuse. And again, the big clues: 1, it's the longest side; 2, it's opposite the right angle. Both of those things mean hypotenuse. And then what about side C? What do we call side C? It's either opposite or adjacent. And notice it's on the opposite side from where the angle is, so that does have to be the opposite then. So the question often comes up, how do I know if it's sine, cosine, or tangent? Well, which one involves the hypotenuse and the opposite? So it's got to be sine. Because sine equals opposite over hypotenuse. It's the only one that includes those two sides. So I'm going to write sine, and then it's of the angle, because it's always got to be sine of the angle, cosine of the angle, tangent of the angle. It's always the angle that goes in. Equals, and then the definition of sine tells me what goes where. So it equals a fraction, opposite over hypotenuse. The opposite must go on top. In this case, the opposite is C. In this case, the hypotenuse is 10. Once I've written my equation, now it's a matter of how do we solve it. I want to get the C by itself. In order to get the C by itself, then, I can get rid of the 10. So I'm going to do that. The opposite of dividing by 10 is multiplying by 10. So I'm going to multiply both sides by 10 here. Now, on the left side, when I multiply sine 70 by 10, I cannot multiply the 10 by the 70. Because sine 70 is actually a decimal. I'm just not calculating what that decimal is yet, because if I do it early on, I can write down this rounded number and it can introduce rounding error. So instead, I just want to leave it as sine 70 until the very end. So when I write this out now, I write it as 10 times sine of 70. And that happens to equal C then. So 10 times sine 70 equals C. Now I can do that calculation. So depending on what type of calculator you're using will change how you type it in. If it's on a graphing calculator, you'll pretty much type it in as exactly as you see it here. You go 10 times sine 70 equals. If you're doing it on a scientific calculator, the order is a little bit different. You would do 70, then you'd press the sine button, and then you'd multiply it by 10. Now, when you do that, if you get the right answer, you should be getting an answer here of about 9.40. And this is usually where a lot of people start scratching their head saying, wait, I swear I did that right. I didn't get that number. Are you in degrees? Make sure your calculator is in degree mode when doing this. On a graphing calculator, press the mode button. On a scientific calculator, well, they vary a lot based on the calculator. But make sure that you can set it into degrees and get 9.40 approximately out of it. All right, and then one little detail-y thing here, you may or may not have noticed it. That 9.40 is a rounded number. And so when I wrote my answer, you notice I used that little wavy equal sign. The wavy equal sign means approximately equal to. So it's showing that we've rounded our answer there. If I had used a regular equal sign, I'd actually technically been saying that it equals exactly that amount rather than the rounded. So just try to start getting in the habit of using that approximately equal anytime you're doing the rounding. All right, next up, number 2. With number 2, I'm going to start the same way I started number 1. And it's actually going to be the same way I start 3 and 4 as well. I'm going to label my picture. So first up, I know A is 30. Notice capital A, so that's angle A, 30 degrees. Lowercase a, so that's side A, is 14. And I'm trying to find lowercase c, so that is side C. All right, now I label my picture so that I then can figure out what I name the sides in terms of opposite, adjacent, and hypotenuse. But only the two sides that I'm working with, because I don't care about the third one. I don't care about B right now. So what do I call the A side, the 14? Notice by the big arrow there, it's on the opposite side. So what do we call it? It's the opposite. Now, notice that changed things a little bit from the last one because we went from a different angle. What about side C? What do we call side C? It's the adjacent. Because it's the one that's next to it. That's not the hypotenuse. Because B would have been the hypotenuse over here. But of course I don't care about it right now. All I care about is the opposite and the adjacent. Because then that tells me whether it's sine, cosine, or tangent. Which one involves the opposite and the adjacent? Tangent, yep. So I'm going to write down tan for tangent. And remember, it's always tangent of the angle. So it's got to be tan 30 equals, now tangent is opposite over adjacent. That's our definition of tangent. So the opposite has to go on top, that's the 14. And the adjacent has to go on the bottom, that is C. So there's our setup. Now a little side note here. Notice I put parentheses around the 30. That was an arbitrary decision. I did it only to show you that whether we put the parentheses in or not, it means the same thing. All right, so now I need to figure out how to solve this for C. But this one can be a little tricky at first if we don't remember, because I cannot simply get rid of the 14 in this case. Or at least if I do, it's not going to help much, because even if I got rid of that 14, the C would still be on the bottom of the fraction. So I need to get the C out of the fraction first. In order to do that then, I'm going to multiply both sides by C. So notice in the last problem, my first step, I multiplied by the denominator. This one, first step, I multiplied by the denominator. Basically always your first step if your unknown is over here in the fraction, regardless of whether it's top or bottom. Multiply by the denominator. All right, so that gives us C times the tangent of 30 equals 14. All right, now in the last problem, I could go ahead and do my calculation at this point, but I can't in this one. I still need to do one more step to figure out what C is. Well, right now it's C times tangent of 30, and remember tangent of 30 is just some decimal that we haven't calculated yet. So if I have C times a number, and I want to get C by itself, I divide both sides by that number. So I'm going to divide both sides by tangent of 30. So we got C equals 14 over tangent of 30 degrees. Now that we have it written as C equals, now we're at the point where we can actually do that calculation. So now it's time to break out the calculator and do 14 divided by tangent of 30. And if all goes well, you should be getting an answer here of 24.25, approximately. I'm arbitrarily choosing to round to 2 decimal places. It's certainly not required since we weren't specified, but it tends to be a nice default spot to round to. Next up, let's do number 3 then. All right, so for number 3, what am I going to do first? I'm going to label the picture, right? Always start by labeling the picture. So in this case, B is 12, A is 8, and C is what I'm looking for. Now notice this one's a little bit different. I'm not given an angle in this problem. I'm also not looking for an angle in this problem, which means I don't even need to use sine, cosine, or tangent to solve it. Do you remember what we do use? Remember the Pythagorean theorem? Just because we're dealing with trig doesn't mean this no longer exists. Oftentimes as we learn something new, the old stuff tends to be pushed aside. I don't want you to lose that because Pythagorean theorem comes up a lot in other different situations. So a quick review and reminder about how we can use it here is worthwhile. All right, so I'm going to be using Pythagorean theorem to solve this then. Now one thing that's tricky about that in this case is up in my formula here I have A, B, and C. In my picture here I have A, B, and C, but they're not necessarily the same things. In the Pythagorean theorem, What does the C represent? It's the hypotenuse. Which means that in this case, it's actually the 12. Which happens to be what we called B earlier. And then A and B, those are the two legs of our right triangle. So that's going to be 8 squared plus C squared. Now that I wrote my equation, now I can go ahead and solve it out. I can do the 8 squared. I can do the 12 squared. And then I can move the 64 to the other side. So now we got C squared equals 80. And then to solve that, I take the square root of both sides. So that gives me the square root of 80. Now, once we get C equals root 80, I actually don't want to leave my answer that way. There's two different ways we can give our answer here depending on which way we're trying to do it. The first way is the exact form. The exact form of root 80 is the simplified form, the simplified radical. So the biggest perfect square that goes into 80 is 16. The square root of 16 is 4. So I could write it as 4 root 5. Or, if I wasn't trying to give the exact form, if I was trying to give the approximate value, I would say that equals the square root of 80 in the calculator, about 8.94. We weren't told which form to give it in, so either of those would be acceptable in this problem. But do note how they differ. One is exact, and the other one is approximate. All right, and then our last one, number 4. What are we going to do first? Label the picture, right? You always want to label the picture on these because it makes everything else so much easier. All right, so we're going to find B is 9, C is 4, and we want to find angle A. And so since we're trying to find angle A, yes, I am going to need to use trigonometry here. So from angle A, what do we call the two sides? What do we call the 9 side?
The hypotenuse.
It is the hypotenuse, yes, because remember that's opposite of the right angle. What do we call the 4 side?
Adjacent.
It is the adjacent. And then, knowing that, that's what allows me to then figure out if it's going to be sine, cosine, or tangent. So, which of the trig ratios involves the hypotenuse and the adjacent?
The sine.
It is cosine.
So,
Cosine equals adjacent over hypotenuse. Now, when I write my cosine in here, remember it's cosine of the angle, because it's always of the angle. So, that's got to be cosine of A. So cosine of A equals, and then it does equal adjacent over hypotenuse. My adjacent is 4, my hypotenuse is 9. So that's why it's then equal to 4 over 9. So where things happen to land tells me whether I'm using sine, cosine, or tangent, and then that determines what's on top and what's on bottom in my fraction. Now I need to solve this. Now let me take you off on a slight tangent here, because I want to bring the concept home. What if I was giving you something like this? The square root of x equals, I don't know, I'm going to make up a number, 5. If you're trying to solve that, how would you get x by itself? We'd square it, right? We'd square both sides, because squaring is the inverse function of a square root. So in the case of our cosine problem up here, I need an inverse function for the cosine. And we actually have one. The inverse of cosine is written like this. It looks like cosine to the power of -1. But conveniently enough, it is read as inverse cosine. We are going to be doing the inverse cosine of both sides of this equation. The reason is because inverse cosine undoes cosine, meaning that the left side is now just A, because I undid the cosine. On the right side, I still have to do the inverse cosine of that. So I do inverse cosine of 4/9. We will use inverse cosine anytime we're trying to find an angle measure. Inverse cosine, inverse sine, inverse tangent always tell us angles. All right, so now I'm actually at the point where I can do the calculation. And again, depending on what type of calculator you have, will change how you type it in. On a graphing calculator, typically, you'll do second cosine. That'll give you the inverse cosine part. And then do 4 divided by 9. If you're on a scientific calculator, you do 4 divided by 9 first, and then do second cosine to get the inverse cosine. Now, if that goes correctly, you should be getting an answer of about 61. So check that, not 61, 63.61. So we got 63.61, and again, this gave us an angle measure, right? So that's 63.61 degrees. Include the degrees there. Now, next up, we're going to be getting into some exact values. So I want to bring home an idea to you about what an exact value really means. So kind of off on a little rabbit trail here. What is the exact value of pi?
3.164.
Now, if you were either just saying or thinking a number, it's not actually right. Because pi is about 3.14159, so on, so on, so on. But can we actually write out the whole number of pi? No. In fact, people that are working on it still don't even know where pi ends. They're still finding more digits to it. So it is impossible to write out the exact value of pi as a number. So when it asks for an exact value, the only way I can describe the exact value of pi is symbolically. And so the exact value of pi is pi.
Weird. Okay.
And so when we talk exact value, oftentimes what we're having to do is we're having to write it in a way that represents how we would get the number if we could actually get that entire thing. Now that's going to come into play with this problem now, because we're going to be looking for the exact lengths of the legs of this triangle. Now this is a 45, 45, 90 triangle. This is also something that I expect that you saw in geometry. It would have been under the section of special right triangles. But I'm not expecting that you necessarily do remember that, because hey, it's been a while. We haven't had to use it in a while. So I'm going to remind you about how we can know what it is. Now I'm going to go through the process and show you what the process is. That doesn't mean you have to be able to replicate this process on your own here like tomorrow, but I do want you aware of the general idea about where it comes from. So let me kind of walk you through, and then we'll get to those numbers, which are the all-important piece of what we're doing here at the moment. All right, so since this is a 45, 45, 90 triangle, it is isosceles. Those two angles are the same measure. And since those angles are the same, these two side lengths are also the same lengths. Now, if those two sides are the same lengths, then I can go ahead and name them the same thing. So, creatively, I'm going to name them both x. So I can then use Pythagorean theorem to find out what x is, because a squared plus b squared, those are my two legs, equals c squared. And here I'm told that c is 1. That's actually because we're going to be going into that whole section on unit circles, and you're going to find the hypotenuse is 1 a lot. All right, so now we can go ahead and use algebra to figure this out, because x squared plus x squared is 2x squared. 1 squared is just 1. And so if I want to know what x is, I first divide both sides by 2. So that gives me 1/2. And then I can take the square root of both sides. So x equals the square root of 1/2. Now that's kind of ugly to look at. I don't want to leave it as the square root of a fraction. So I'm actually going to do the square root of 1/2. In order to square root a fraction, you square root the top and the bottom separately. So the square root of 1 is 1. And on the bottom, the square root of 2, well, that's just the square root of 2. Now remember, I don't want to leave my answer in this form though, right? Because we never want to leave a radical in the denominator. Does this problem seem slightly familiar? Maybe the first problem we did at the start of class today. I multiply top and bottom by the radical, so I multiply top and bottom by root 2. And so that gives us root 2 over 2. That's why we did those problems at the start, because you actually needed to know why does it become that. So, x equals root 2 over 2, which means we now have this picture of the triangle. And this you should copy down into your notes because it's going to be a nice little reference to look back at. And as you're doing that, I also want to illustrate how that can let us figure out what sine and cosine are. These are actual definitions of sine and cosine, because sine and cosine definitions start with the assumption that your hypotenuse is 1. And then anytime it's not 1, we are just stretching it or shrinking it accordingly. So sine of 45 degrees. So going from one of the 45 degree angles, it doesn't matter which one since they're both the same. Sine, remember, is opposite over hypotenuse. So then that would be root 2 over 2. That's the opposite over the hypotenuse, which is 1. Now that looks kind of ugly. Root 2 over 2 over 1. But thankfully it cleans up pretty nicely. Because what's anything over 1? It's just itself, right? So actually it's just root 2 over 2 then. So that's actually the exact value of sine of 45. If right now in your calculator you did sine of 45 degrees, and then you did the square root of 2 and divided it by 2, you get the exact same number out. The only difference is that when you do that on your calculator, it's giving you a rounded version, an approximation. Whereas when we do root 2 over 2 and write it that way, this is the exact form. Again, going back to that idea about what the exact form of the answer would look like. All right. And then finally, cosine of 45 degrees. So if I'm going for cosine, that means I pick a 45 degree angle. Cosine is the adjacent over the hypotenuse. So again, that's going to be root 2 over 2 over 1, which is just root 2 over 2. So sine of 45 and cosine of 45 degrees are both exactly root 2 over 2.